Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischman Memorial Project. So welcome to this O-Day Flux Capacitor. Thank you for joining me on this Sunday the 17th of March and top of the morning to you or afternoon in California here, and good evening for those in Europe and in the UK. And good morning to tomorrow for those in Australia. Hi, DIY Projects with Chalxis, Tony Yaboni, EBB, Creating Awareness, Riandathal, Pernicola, Haukland, Ren van der Wald, D2105K, Open Source, Matthew Reynolds, hi, Luke Threadgold, Artifact, Alex Del Castillo, Gordon Doherty, Vom Altholt, and Simeon Hein, Gaia Zyme. We have a good quorum in the house. We have Synth Art, many people. Nick Knock, hi, great to have you here. Hi Tammy, YPi01, Stuart N Overwound Games, Bo Sinclair, and Philip O'Folian. I'm sorry if you can't say that, but good evening to you. Cody Taylor and Harry. So, hi Stephen F. Excellent, great to have you all here. Well, I need to go and have a shower, and I'm going to play you the first part of a series of videos that I took over the last couple of days on the SEM here in the Magic Sound lab of my fellow MFMP director, and that is one Alan Goldwater. So a huge thank you to Alan Goldwater for letting me use his SEM these past several days, and also a thank you to all of the people that have supported this work over the years, because I think whilst this video is very raw, so what I had an opportunity to go out with Alan and walk the dog in the nature reserve. I said, Alan, I've already committed to putting something out today, and I kind of want to get this out as soon as possible. I don't want any risk for this not to be public, but I think hopefully, even though this will be dirty and raw as a presentation, you will get that the sacred geometry fractal structure is the seed of life. It is able to transmute matter, and the evidence that has come from this particular sample from Binjuan Huang, he has literally meters of this material, and he could send it to any lab in the world that needs to have some corroborating evidence. And it is so phenomenal, it beggars all belief. It precisely shows how this works. It precisely shows how it can damage material. It is exactly a fractal structure. It is exactly the sacred geometry. I couldn't have wished for a better sample. And it is, you will see, synthesizing matter. I don't think there can be any doubt. When you see the images that I will share with you this very day, you will have no doubt that we have the power to transmute matter just using sound, cavitation, and water. It is a deep honor to have been able to observe this, and it is my pleasure to present this to you today. So first off, there's going to be a 30-minute video, and I'm going to go and have my shower, and that will be showing the first part of the analysis of the outside of the inside collapsed pipe from Binjuan Huang, and then I will come back and I will walk you through the rest of the material that I captured in terms of images, and we can have a long discussion about that and the implications of it. And then over the coming days I will edit the many hours in fact of video and put the transcripts together so that this can be put out with the raw data. But for me, this is utterly conclusive. Utterly conclusive. Of course, I may be wrong, and I would like anyone to delve into this, both looking for other things that you can see that I've missed and other things that might point this to being a perfectly ordinary set of observations. But I really think this is the wheel within a wheel within a wheel. It is consistent with everything we have shared over the last 5, 6, maybe even 7 years. And this is the God's toolbox, and we are at the new dawn of an old age. And Alan was asked by his darling wife to find me a green shirt today, because we're celebrating Paddy's Day, because she is heritage from Northern Ireland. And he found me this shirt, and it's all about the end of the world as we know it in 2012, right? In 2012, with this big explosion here, living with this kind of toroidal zone and this circular area out here. And I think this is highly appropriate because the project was started in South Korea in 2012. And I've said for quite some time, it wasn't the end of the world, it was just the end of the world as we knew it. And I think really we are rediscovering what the ancient people knew. And I think this is going to be so clear. So if you know anyone at all that has followed this along, because it's going to be straight into the data after this video. In fact, the video itself is going to be the data as well. But if you know anyone, bring them to this podcast. I want as many eyes as possible on these images, because it nearly had me in tears. The certainty a child will be able to know that this is the way it is, and that we have an incredible tool that is the gift of nature, and is the most powerful tool, I believe, that man has ever been able to be to grips with. So without further ado, I will switch over to the video, and I will go and de-sweatify myself. So thank you very much. I'll see you in about half an hour. Here we go, and I'm going to fire away. Please tell me just before I go if there is any problem with the sound here. Here we are looking at the 210B DHX-2 sample that was given to me in Taiwan, 29th of December 2023. So here we are. This is looking at the sort of apex. If I come over to the side here, you can see that is the edge of one side of this collapsed pipe, and if I move it all the way over to the other side, you can see this is the other edge. It has these kind of striations on it, which is interesting. But we're going to go into the central point here, approximately there. And we are going to do an autofocus, and it would appear that there are some fairly regular spots all over this pipe, which we are going to investigate. So we'll take one shot at a distance here. We're on BSE at the moment. That gives us an opportunity to see different elements there as different colors. So I imagine that the bulk of this is copper oxide, which, because of the copper is bright, is the sort of light gray background. And there appears to be these darker spots, which are going to be lighter elements. That is, lighter in terms of their mass. Let's go into this. Times 200. This is kind of the scale that my the dyno light has been able to capture over the years. Goes up to 220, in fact. Very regular spots here. Interesting to see what the morphology of those are and what the elemental constituents of them are. So I can actually turn off the image optimization here because I actually want the raw data here. I can post-process it later. Now this is interesting because this is on the radius of the material that is stretched, you might consider, and I can see there are linear cracks along here. Now is that the material falling apart as the pipe collapsed? Don't know. Let's go in here and see what we can see. Well, these are definite spots of some type. Definitely different material. What are they? Interesting, I can already see this is almost hexagonal in geometry here. These are almost like vertebrae. Interesting. They're like little cookies. This is flat on and these are on the side. Very interesting. Definitely, this is like a round one, and it's like a Oreo, but fat Oreos. Almost like a vertebrae, as I said. Interesting. So, we want a flat on one, a side on one. Let's move around, see if we can get a good variation of them. It's like a twisted knot. It's like a ball of them. Wow, look at that. It's like a real old bundle here. We've got flat, side. It's not a bad selection there, is it? And something heavier over there as well. Okay, well. Curious little things. Is that really better? What are these little structures? They literally look like Oreos, look. Oh dear. Are they two toroids stuck together? How curious. Okay. Let's see if I put the secondary electron here and see if we can get something that's showing more of their structure. Topology. So I've got a mix of backscattered electrons and secondary electrons here, using this image. Wow, that copper surface looks a little bit ropey to me. Now, are these coming in and damaging it? I don't know. I think I like the backscattered electron shots here. Gives a little bit more comprehension of what elements are what in this process, whatever that is. So I'll take that. And we're going to move this over to the SEM EDX detector to have a look at what these things are. Now, I imagine the background is going to be copper. And these are going to be something lighter, but what are they? What are they? Let's find out. So firstly, let's see if this really is copper on oxygen. Looks like it's copper and oxygen. Yeah, that's pretty conclusive. Copper and oxygen. Yep, nice number of counts. Give us a good answer. So what, pray tell, are these? Are these some sort of phosphorus compound? Really is just copper and oxygen. Atomic concentration. Cu2O. Somewhere between Cu2O and CuO. So somewhere between cuprous and cupric oxide. What are these things? Let's choose this one's edge rim. What is that? Well, it has a lot of phosphorus in it. Well, there is... Okay, is it really phosphorus or is it actually... I don't think there's any zirconium in there. I think it's got confused. No, there's no peaks up here, so I don't think we're seeing zirconium there. And I don't think there's any tantalum either. Silver. There is a peak here. What is that? Maybe. Don't see the peaks down here for silver. So, is that carbon? I think it's carbon. Carbon and phosphorus, a lot of phosphorus. So some copper pipes are treated with phosphorus. Could it be because of that? Does look like this is not so damaged, and this area where this is coming is damaged. It does look like these are affecting the copper. This is the kind of untouched area, and these are being affected by whatever these are. Let's have a look in a line scan. Maybe that might be appropriate to do now. Let's take another sample on the edge of this one, shall we? Like there. Well, it's pretty consistent as to what they are. Really not sure that has silver in it. I would suggest not. It's definitely not tantalum. Come on, don't be silly. Need to re-sample that one. Yeah, I need to change the titles on these. Okay, so we're going to look at this first by looking at the copper. So we'll have a quick look down here. See what that is. And no surprise there, it is copper and oxygen. Maybe with a minuscule amount of carbon. So copper did itty bitty bitty phosphorus. And oxygen, we'll have a look at what the edge of this one is here. So we'll look in the middle here, because then we won't get anything coming from the boundary around it. Wow, that has a much higher degree of phosphorus in it, otherwise it's got the same constituent atoms. They literally look like fat Oreos. Although they have a hexagonal kind of external structure. Are they two toroidal structures coming together? This is definitely looks like it's embedded in this one too. In fact, they all look like they're embedded in to a degree. You can see what it is on the edge of one of these things. I think this is probably good for the edge. Again, very consistent. In its makeup, in terms of the key elements. So probably I should do a map, shouldn't I? Where would I do that? I'll do one on here, I think, and one on here. Yeah. I could do a line scan. the line scan, and I think what we'll do is we'll take our line here and we'll just move it across here. Across the center line of this one. Yeah. And to see how many points. Line scan. Okay, close. Let's do an acquire on that. Really, scandium? I don't think so. Just not there, is it? Don't think there's scandium there. So the oxygen goes up and the phosphorus goes up. The copper goes down and the carbon goes up a little bit, doesn't it? So that is the line scan completed. I'm going to capture this set of data into a new report. So a bunch of stuff there. And we will also add in this line scan. So you can see it like that. That's how it represents it. Okay, we're going to have a look at a little bit more area here. Interested to see what this little thing up here is for a start. Won't go too far over. This looks a bit like a fleck of iron. But because it's lighter, it might be heavier than copper even. So I have to see. I think it's quite useful if I actually take this into the EDX. And we will have a look at what this actually is. What is this? Well, it's just copper. Maybe a itty bitty bit of carbon. Pretty high proportion of copper there. As you can see, that is a pretty high peak. So it's just a lot less oxide. We will take one here. Antimony? I don't think so. I don't think so. No. And not tantalum. Stop it with the tantalum. Just copper, oxygen, and a bit of carbon. And this is our phosphorus rich whatever it is, it's a Oreo, Fat Taurus. Let's just get a sample of that now. And that's that phosphorus peak. Don't think there's any magnesium in there. Gold, I don't think so. I think if anything, that is carbon. Not gold, don't be silly, it's carbon. So we'll have a look around a little bit more. So this is just extra copper rich. Here's one of these Oreos that's been broken. Now, what are these little puppies? These spherical structures in here. What are they? Are they really spherical? Do look a little bit spherical, don't they? So we'll have a little look around a bit more. Could these little Oreos actually be from a much larger structure? Look at this Oreo here. It's almost got some vortical structure to its substructure. Definitely some substructure going on there. Not convinced what. There's a much smaller one there, look at that. Interesting. This one's round and it's kind of like got that one intersecting it. Much larger one here, isn't it? Practically 10 microns, maybe bigger. Starting to form a kind of ball shape, isn't it? Almost like a... Well, it's interesting, isn't it? Can we risk trying to change this to a mix here? It's going to give us anything useful? Don't know. Maybe. Is that better? Don't know. Almost looks like a fir cone, doesn't it? And a very round variety of fir cone. Really embedded in there, isn't it? There are a lot of these structures. A little hard to see with this particular setup. A very fat one there. Definitely got some sort of form emerging from these. Like to embed themselves. don't they? Look at that. Lots of embedding going on in the copper oxide. Could we argue that's spiraling around there? Maybe. Let's have a look at a few more. See if we can see a pattern emerging. Let's find. Ooh. You see this one here definitely looks like it's got something heavier at its pole. Wouldn't you say? Is that as in focus as we can get? Don't know. Really does look like it's maybe spiraling around. And at the peak here it has this object here. So I think I'm going to have a look at that over in the EDX. So the bulk of the material is probably the copper phosphor and oxygen, as we've seen before. Don't think there's any gadolinium in there. That is an iron peak at the top of this potentially vortex-like structure. No tantalum. Come on, don't be silly. Wow, okay. This is interesting. Did whatever caused this either gather or synthesize this iron? And is it these iron pieces that are then gathered up into other structures that form what we have been seeing? Not out of this reactor particularly. This is the DHX-2. But could a similar process be going on in other reactors, the synthesis of iron? But that is very clear. We are talking about 18% in this case. 18.5%. Boom! Wow. Okay, so absolutely everything came in the right order in this journey as I analyzed this sample and the previous sample of the magnetically extracted material from the VCS5RT from 2021. Everything came in the right order. And so, boom! Okay, now I'm not getting paid by either Norton or by Oreos, okay? Just want to clarify that. I just say what I see. And I'd like to say thank you very much for everyone getting the message out there. We've got the largest number of viewers I think the channel's ever had, and I think this is an appropriate time. Okay, so that is just a half an hour section of probably 7 hours of video. Needless to say, if I was going to say anything today, I couldn't have done all the editing on that. But what we're going to do is we're going to go through the images that were captured and maybe look at some of the SEM analysis. And then I'm going to step in because over a couple of days, what happened was I saw something, I went and slept on it, and then in my head I was rotating things around. I go, oh my God, that's that. And then like a little bit later I'm going, oh my God, that's that. And then I then knew kind of what to look for, and it then allowed me to look at the mass of material that's on this sample and identify when I'm looking at things, and even in previous images that you've seen in that video that I've just shown you there, what was actually going on. And it tells a beautiful story. It tells a story of creation of these structures, but also their demise and what they do in between. And they are, my friends, they are a flux capacitor. Yes, they are a flux capacitor. So if you can imagine a normal capacitor is able to store electric charge, that's a capacitor. What is a flux capacitor? A flux capacitor is able to store magnetic charge. And this is precisely what was detailed in Mikhail Solin's 1992 patent. He says you get two solitons of two different magnetic charges. They cluster, they form spheres and tubes in which nuclear reactions occur. And matter comes out of these things. You're going to see all of this in glorious detail. And like I say, I will interject with imagery where you can see how this fits with the sacred geometry. Now, I haven't done my best job on that. I just did it rough and okay, that's that. I did it in my head. So you'll see the 2D actually image made by Tony Giabboni overlaid, and you will see that that is what it is. And in future videos, I will do more accurate orientation, because the structures themselves are for very good reasons, which are easily explained by how they are clearly acting, the way they come into contact and crash in and burrow into the surface. This means they're typically at a particular angle or flat on, depending on how they came to their demise. And so I need to rotate in 3D to align it exactly. But you'll know that this is the case. Okay, so here we have the second screen here, and maybe you can see on the left, this was the first image I got, the first glance I got of this particular sample. And I think we can safely say at the end of this that probably it wasn't necessarily 700 atmospheres that caused this to fail. It was possibly the interaction of these things on the surface. Now, if you look at this, it's a 1mm scale here at the times 100 magnification, and there is effectively 4mm squared on here. And you can count the number of large structures, and you can count the number of small structures, and even smaller structures, as we will see. But you can then do a calculation for the amount of structures you can expect on a copper pipe of this type. But what I will say is, as I reiterate, if there is anyone out there in the world that has the tools to verify this, and they're a proper bona fide institution, and they want to see this for themselves, I would suggest you reach out to Binjuan Huang and ask for a sample. He's got lots of this material, to the best of my knowledge, because large sections of the pipe were collapsed in this way. The collapses only occurred when there was excess heat, and the emission in their understanding and observation of production of carbon, neon-22, and oxygen-17. As you will see today, there is all of the typical elements that you see in interstellar space being synthesized. That indicates that this is the flower of life. That indicates that we can use this technology to go to a barren planet, which is in the habitable zone, and use whatever material is there to synthesize the matter for life. And that is not just on the actual elements that are solid, but this will also be producing gases. And because it's yin-yang, there will be a lot of hydrogen produced, particularly if you're using lower mass elements, and then it produces the spread spectrum of the bulk of the elements that are in your body. So this will enable terraforming and the improving of atmospheres on other planets. So this is just absolutely mind-boggling. So let's get on with it. Okay. All right. So this is O-Day Flux Capacitor, and this is the boring bit where we go through our slides here. So here you can see we have an arrangement of structures, and why have I just jumped right to the end? I don't know why that happened. Give me just a second to fix what's going on there. I'll put it on my mugshot. See what's going on. I've ordered that. Should be in date created, so that you can see it in the exact order that it was produced. Let me see if this is right. Yeah, okay, this looks right. Yeah, this is right. Okay. All right, I'm going to make some commentary on some of these, particularly the carbon strands that you'll see. And I'll be referring to other presentations you will probably need to do the homework and go and find those because I haven't laid the presentation out in this way. But that is what I believe is going on, and I may be wrong, but let's see. Okay, so this is our first image here. Now, just want to talk about what you see down the bottom here. In the SEM software, if you looked at the video, I didn't change the name, so I will have to correct this. It's not like I'm faking anything. On the video, you will see that all of the initial images that I take were named for the previous sample, the cracked microsphere that I've already published. Okay, so you can see in this maybe 25 millimeter squared area here that there is a vast number of these structures on here. A vast number, okay? And the majority of them fit to a particular size, and it's very interesting because it's very clear that Ken Shoulders was right about the particular size that is made by these structures. Okay, so we're zooming in here, and we're zooming in. We've changed the type of observation there, and we're zooming in. And this particular one here took my interest because it is a kind of helically wound carbon structure. And this is similar to the kind of structure. I'm going to remove my mug shot here so that I don't... there we go. No, that's the wrong one. That one? Yes. I'm going to remove that one. So anyway, this structure here, where you can see my mouse, it's like a helical twist. I believe this is the collapsed coherent matter that have come out of one of these structures, maybe one of these ones that have died in the nearby area. But this is the kind of thing that would have left the interference and interaction on the aluminium foil that I ran for about 90 seconds in a coherent matter process called Ultra. It is an ultrasonic experiment that you can do from the age of 3 years old, and go and look at that on the Martin Fleischman Memorial's website. But in one case, there was an interaction, I believe, of something which you can't see, but it's left a particular helical type interaction in the aluminium. And I imagine it's these kind of things that are doing that. But anyway, you can see here what I call the Oreos. They seem to have a polygonal outside. So we've got 1, 2, 3. I'm going to zoom into that maybe. We've got 1, 2, 3, 4, 5, 6, 7 maybe. They can have a different number. And this is flat on, and you can see they have a substructure in them. And then this is buried into the side, on its side. So they said they're very well lodged into what is predominantly copper oxide on the surface here. And of course, CuO, I think it's cupric oxide, that is black and shiny. So whilst there is a lot of carbon in here, some of the black and shininess can be explained by the fact that it is that oxide or varying oxides of copper. But of course, something very violent happened with this particular structure here, and we're going to look at what that kind of is. So if you go and look over here on the right, the first analysis came back as essentially copper, oxygen, and phosphorus. Now, phosphorus can easily be synthesized in low-energy nuclear reactions. Is it synthesized in this case? I don't know, because we don't know whether the copper feedstock had some passivation or some cleaning, maybe with phosphoric acid or something. It is sometimes used in copper piping, but whatever. I'm actually not so interested in that, and as you'll see later, it might actually point to the importance of adding phosphorus. Phosphorus 31 obviously has spin, because it is well, basically it's 31, right? Okay, so I can just check that for you. I don't want to say anything wrong. Yeah, so give me a second. So on the nanosoft.co.nz, you can go to show element data, and we go down to phosphorus, wherever it is here, phosphorus. And you can see it has spin half plus, So my understanding is that these technologies will take up magnetic material or paramagnetic material or spin material, which is a lot of material. If the material is not actually, you know, you can actually, by ionizing it, you can get it involved with the process as well. So anyway, that's that. Okay, so moving on, there's a different view of that same structure, and we will come back to these images because I realized something after I realized something else, that these were showing us something very, very important. But at this stage, I'm going to say, can you guess what it is? And we'll see if you can guess what it is. Okay, so I took a whole bunch of images there, and I took a line scan across here. If you looked at the video across there, and we can see that in the line scan, your phosphorus and carbon go up and your copper go down. And so that's that. And so anyway, you see the real-time data there in the video. I'm going to pull that back there. Okay. So this wasn't so interesting. Wasn't very interesting, that particular one. It was just copper, oxygen, and phosphorus with a itty-bitty bit of carbon. More copper in that. These weren't particularly interesting either. I think one is just a hole and it's the shadow, and this might be a circular thing, but it's nothing really of interest there. You can see there it's just the same kind of material. Although this is very rich in copper, you can see here it's 89.96% copper. And why is it balled up? One could ask a question about that. But anyway, so the money shot in the end and the boom in that last, or the first of the videos in this sequence, was actually this one, looking at this piece here. So there's like a one piece that way and one piece that way, or whatever. But this particular piece turns out to be very rich in iron. As you can see here, 18.53 by mass concentration. Okay, and what I found out since is you get a lot of things coming out of these things, and you'll see it later. And this here, and I will explain what I believe this is although I didn't look at it, I can tell you that that is essentially a disc of iron from looking at many other examples here. So you'll see that there are many flakes and pieces of iron here that come out of this process. And I expect that more resonant structures like this will capture this iron and actually make it part of their body, like this has made copper, oxygen, and phosphorus a part of its body. And so that's where you would tend to, in my view, potentially produce these iron pieces. Okay, these iron crenellated microspheres, which we've now found have magnetic charges inside them. Okay, so we've got these fat Oreos here, and then there's an interesting little sub Oreo here. But I don't think this is. I think this is a section of iron, and my understanding is that these are born inside these sub Oreos, and you'll see what I mean in a little longer. Okay, so now I want to just hold this on frame here and just see if anyone can work out what I'm going to say. I'm going to just give a couple of minutes for people to think about that image. Not a couple of minutes, but at least a little bit of time. Can anyone work out what I might be talking about with this image? No? No, okay. Right. Well, I will come back to that image. Rose flower portal. Just like the Tor structures, flower of life structure of 4. No, it's gonna okay, all right, we'll move on, and we'll come back to it. So here's that same structure in combination with a couple of these these Oreos, when they effectively slow down, if they don't freeze out, the coherent matter, in my view, doesn't freeze out in the Oreo state. they sometimes end up a bit more like vol au vents, you know, puff pastry type things. Now, I asked you what this one meant. Does the one down the bottom here give you any indication or better understanding of what it is? What's going on? Because I believe what you're seeing here, and I'm not going to go into the full detail, but these two belong together, and so as above, so below. Right, okay, so I'm now looking at another one, and again, does this help you understand what's going on in these two? This one here. This is the one where we actually found the iron in the top, up here. Can anyone guess what I'm trying to put? One looks like rotated 90 degrees, not so bad there. You're getting the idea. I see a hexagon, yin and yang magnetic flux. Yeah, kind of getting there. Vortex, anti-vortex pairs. Oh, getting closer. I think one of these is a vortex and an anti-vortex pair. And I think you'll find that these are the vortex and anti-vortex pair, drum roll, that was inside this one. And they've come through these gaps here. And I'm going to show you, I realize this actually later, but I'm going to show you how I can, you know, with previous images you've already seen how this works. So you have these two coming out of this one, and this one is emerging from the bottom of this. So what this tells me is the outside is less stable and less strong and less capable of surviving than the structures internally. Okay? And that these can be borne out. And you see this in the Moscow Nuclear Physics Institute of the inside tungsten wall of a tokamak fusion reactor, where something impacts it and it produces this flower of life type dendritic structure from a point. And that is exactly equivalent to what we observed on the inside crust of the Lion reactor. And previously it was observed by Ken Shoulders, where you have an exotic vacuum object impact a surface. It breaks up into multiple structures, and then they break up into multiple structures. And as they go, they deposit carbon. You will see everything in this set of images. It is done. And a child will be able to know that this is the truth. Okay, right. So like I say, this Oreo or this vol au vent has come out of this one. The other one didn't make it. You will find that these are mixed elements here later on in our study here, and these are likely chunks of iron. And these have come out of this one, and you can see that they've survived a little bit longer. Okay, all right. So this one is emerging from this bigger structure, and this disc here, although I didn't analyze it, might have been fairly iron rich, and you're going to see that later on. I looked at this particular piece over here, and it was copper, just the usual mix. Okay, so here's a close-up on one of the little vol au vents, and you can see there is a vortical nature to the flow pattern on here in this overall structure. Okay. I'm going to say we've got 172 viewers. This is by far the most we've ever had. So thank you for spreading the word. Keep it going. This is going to be probably one of the most important streams the project has been able to deliver since its inception. So thank you for joining us. Okay. All right. So did I look at that one? Yes, I did look at that one. So I was looking at the tail here to see if it was any different. And in this case, it wasn't any different. So we will move on. Now, look at what is going on here. We have two that are trying to get together, and then this. Is this part of this structure? I don't know. But look, you have these vortical rings of material. I kind of wish I'd analyzed this, because I can pretty much tell you, and you're going to see it later on, that this is this blend of synthesized matter, and it's literally spilt its guts. And you're going to see this spilling of its guts, total spilling of their guts. And it's almost like another torus has come in here. You're going to see something so unbelievably beautiful later on, and it's going to be totally explicit what is going on. So this particular sample here, we looked at this. Oh, sorry. There was something else that I looked at, but you'll see it on the next video. I looked at the chunk on the top here, and it's saying copper, phosphorus, and nothing was revealed until it was necessary to be revealed in this whole process. But what I did is I looked at this plate, and I've seen this kind of thing before, and it's I think also indicated in Matsumoto's book, Steps to the Discovery of Electronuclear Collapse. Okay, and what he shows is a carbon film with iron. Okay, and in this case, this isn't a carbon film with iron, but it does have aluminium, silicon, phosphorus, sulfur, chlorine, titanium. Titanium, we know, is possibly the fusion of carbon and oxygen. In fact, in the ratio of CO2 makes titanium. Aluminium you get out of different isotopes fusing of carbon, oxygen. Silicon is the fusion of carbon and oxygen. Same with phosphorus. And then sulfur is the fusion of oxygen. And so you can work out all these things, and you can look at nanosoft.co.nz to find out what the ratios are. So you can see here the atom percent and so forth. But the vast majority of this by atom here is carbon and oxygen. And in Matsumoto's work, he said, like, on the outside, you get hydrogen, carbon, and oxygen synthesized on the outside, and the heavier elements like titanium and iron and so forth get synthesized in the inside. You can see here I actually am looking at this little blob here, and probably it's capturing some of the material on the outside there. Okay. Right, so, sorry, the first one may be an area, and on this one I'm actually looking at the blob there, and you can see the titanium's very, very high, okay? This area here. So I'm over this area here, I am looking at titanium being by mass percent, 22 mass percent normalized, 22.26%. So that is a hell of a lot of carbon and oxygen that are fused together there. Okay, all right. And you can see it's like loads of stars. So these are little structures that are nucleation points, I believe, in the synthesis process that have led to the synthesis of this blended material. Okay. 173, well done, guys. Okay, so we have a little Oreo here, and I think these Oreos that don't end up in a vol-au-vent shape, a slightly inflated one, it's because I think that they are still, they actually phase change from coherent state to ordinary matter so instantaneously they don't get a chance to expand. Some of them kind of slow down, okay? So, right, so we got another bunch here, and again, we can see the Oreos are coming out of, this one is coming out maybe of this one, and this one's coming out of this structure. So you can see different quantization levels here. Did I look at that one? I did look at that one, yes. And so again, at the moment, I'm just looking at anything, and I'm kind of getting a pattern for what these overall things are. But you can see there's a sweeping material going in here or coming out or whatever, bearing in mind that this is one of these structures that's broken up. Okay, so there's a seemingly a pair here, maybe or not, but there's an Oreo here, and I look at this fleck that's on the side of this, and again, it's actually basically pure copper, and of course that's not surprising because we are running through copper pipes. So yeah, by mass it's 70.29%. Now, we come and look at this one in a minute here. So I'm just looking around the debris field here, and you can see just how many Oreos there are, right? And then there's little structures beyond that. In this case, not this case, I didn't look at this, but again, in this case, you can see the Oreo has broken out, and this Oreo is broken out of the larger structure. And, it's got a trail of stuff that it's kind of almost pulling into its pole, and probably that's exactly what it is doing. Okay, so this one we have a look at a little bit closer. And what do we see? Well, we're getting still a more detailed understanding of the base elements, carbon, phosphorus, copper, and oxygen. I kind of forgot how to use the SEM at this point, so I didn't actually ask it to look for other elements. So I disappointed myself, but later I realized it was just down to my periodic incompetence. So anyway, so I look at these various bits here, and then I look at the end of the next piece here. and so forth. Right, now, in the next one, you can see there is a light colored object here and a dark colored sphere here with a kind of trail. So I think this is very interesting. This looks like a structure has collapsed in here and the rest of the material has gone away, and it's just left potentially a couple of the cores or the core detritus. And when we look at this, indeed we see on the black side this black sphere here, we see a blend of the normally synthesized elements that you're going to see much more of: magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, iron, and of course carbon and oxygen, okay, along with copper. So this has traditionally organic materials mixed in with inorganic materials and the source material in one blended sphere. How is that possible? How is that possible? Okay, moving on. I actually did a map on this. I took another study point on the white one here, and again it's the same kind of elements in there, but I guess it's more skewed to copper, so it's giving us a more detailed look at that. Okay, so hold on, what is this one? I can't even see it. I can't see it. It's not high enough resolution in that shot, but anyway, you can see it in the video, which I will publish. Okay, so I then take a map of this particular area here, and you can see very clearly, I think if I take a close-up here, and I then take a section of that close-up and build a map, and you can see very clearly that magnesium, this sphere has clearly magnesium, it clearly has iron, and the iron is in that, but almost in a vortical nature there and there. And when you actually look at it, this resolution, you can see a little bit of twisting. I haven't done any image adjustments on these, so that will probably come out. But yes, calcium and potassium, these things are often co-located because they're just one proton away from each other. Magnesium, sulfur, silicon, aluminium. So of course, magnesium is one proton away from aluminium, and aluminium is one proton. Sorry, what was that? 24. Yeah, sorry. Then silicon, 24, 25. Yeah, then silicon, then aluminium, then we've got sulfur there, and then chlorine. You can see these are all located in this object, this spherical object that has kind of a vortical tail to it. Okay, so we're starting to maybe understand what's going on in the real guts of these structures. Okay, this one may be just a cotton fiber, but I have seen something similar in the Lion reactor. I'm not convinced this isn't a cotton fiber, so I think we can probably ignore that. And I'm at the end of this particular Word document, so I'm going to switch to my holding frame here, and I will go and get the next Word document for us to look at. Okay, so it would appear that I did look at it, and indeed it actually looks more organic because it has carbon and oxygen and sulfur, chlorine, potassium, and sodium. So we don't see a lot of inorganic material in there other than some contamination for copper. So my conclusion is that this indeed is a cotton fiber or something similar. Okay, piece of contamination. Okay, this, however, I believe that this here is the coherent matter wave, and this is similar to another coherent matter wave that was found in the Henk-Weger experiment, which looked like this, it was much more pure. It didn't have all this other detritus, but then it's in a plasma system rather than in a water cavitation system. So that is not surprising. It also looks like the same kind of thing that would have interacted with the aluminium foil in the same ultra experiment that I was referring to earlier. And so I think this is a signature of the effect. this would be coherent matter when it's operating, and you can see it's associated with this broken up structure. And it's almost like this one started spitting it out, and then it just blew up and left its detritus. You can see here the interwoven mesh of this, and are these the two halves, or is this one larger EVO, and this is the material that got deposited as it overall broke up? Okay, so what have we got in this? Well, we've got a lot of things in this area here. Just this area here, we find carbon, oxygen, chlorine, sulfur, titanium, iron, sodium, magnesium, aluminium, silicon, phosphorus, potassium, calcium, and a very large amount of titanium. 17.55% of titanium in this particular structure that has this kind of like star-like presence of little pockets of these various synthesized elements. So really, really fascinating to see this in a hard sense coming into crystal view. Okay, so anything more on that one? Yes, I did. I think I did another sample. Okay, so unless it's a close-up sample of that, I'm just showing it. Okay, right. So there was another one here. I didn't look at that particularly. Here is a complete debris field of these the larger structures, and we're going to talk about exactly how large they are, and they are quite well quantized. But this is the outside, and where this is actually is on, how should we put this? It is on the apex. So if you remember, the Binderin Huang copper is like this, and it goes up, down, and in. And maybe I've got a photo on my phone I can wave at the screen. Maybe I can do that. I've got a photo there. Let me see. It's the sort of thing I might have done. Although maybe I didn't this time. Yeah, okay. That's my bad. All right, so I will get you a photo of that. But basically, it's like that. Okay, and on the top, the apex of the large curvature bend, this is where these are. And so I think a lot of damage was being done at the top there, because you know what's going on here is extremely violent with what I believe are coherent matter structures. Okay, so and here in this case we've got these little balls. You know, this little ball here is quite cute, and this one here is this trail of fluidized material that's leading up to this structure. Is it relevant to this structure? I don't know, but anyway, it's there. That's what it is. Now this structure looks like an ejector. And when I took this, I didn't actually realize this little chap down here. But look at it. It is spewing out of this structure. Oh, you can't see. Sorry. Right, sorry. All right. I'm not sharing it. Silly me. Right, there we go. So this is the area I'm talking about, this debris field. And it's just a mishmash. And when Alan Goldwater looked at this, he says, it looks like a piece of fabric. And I'm saying, yeah, it kind of does. And fabric is interwoven kind of mesh-like structure, but it isn't quite that. It almost looks like wheat chiefs, doesn't it? You've broken up a bunch of toroidal wheat chiefs. Okay, so let's move on from that. These are the little ball that I was referring to, which has some geometry to it, and it's well embedded in there. It looks like a ball of string, doesn't it? And this one here is this trail of fluidized copper oxide. Is that relative to that? I don't know, but we're going to see some evidence later on that this is incredibly clear. Yes, you're going to see it soon, open source. You might be just a little bit behind the stream. Okay. Now, this one here, with this material here, I was interested in this material because I just thought, oh, I'll look at that. But it was only later that I realized that, look at this. Boom! This material is all coming out of this one structure. How is that even possible? How is that even possible? Well, copper is 63 and 65 nucleons. And phosphorus is 31 nucleons. Of course, if the bulk of this really is carbon, okay, then that is only 12 nucleons. This is exactly what we observed in an iron-rich crenellated sphere in the work of Henk Uren in the Vega experiment. But it was previously observed by Dr. Takaaki Matsumoto. So thank you and full credit to Dr. Takaaki Matsumoto for observing this first. But here we are really seeing the thing that's doing the work and what's coming out of it. And this supports the claim of the 1992 patent by Mikhail Solin that magnetic charges, that is a flux capacitor, is able to gather and crush. And as Luke Zietner said in 2019 at ICCF 22 in Azizi, and you can go and see his presentation on the Martin Fleischman Memorial Project, he said that the magnetic flux can reach 50 million Teslas. That's 5 orders of magnitude more than the inside of our sun. It's the same magnetic pressure as you get in a pulsar, which is a type of neutron star. Okay? And these are obviously, effortlessly produced in relatively simple apparatus that Binjuan Huang is using to create excess heat. And the excess heat must be coming, one might assume, from these nuclear processes, which are very clear. And so, and effortlessly doing this. So this little guy here has had nuclear reactions, and this is what Solin said. The magnetic charges accumulate, the toroidal magnetic charges accumulate into spheres, and inside those spheres, nuclear reactions occur, including right down to the decay of baryons. Okay, the decay of baryons. This is exactly what Kladoff said. You can get complete collapse of matter into field forms of matter. That's what he said in his 1990 and 2003 work, okay, on his website. And so you can see, if this has to all come from in there, it implies that either there is a structure in there that's converting the copper into these other elements, as you'll see what they are in a second, on the fly, or that the atoms are trapped in there and they're completely stripped of their electrons, and the fusion is going on or whatever, and it's only at the demise of the containment field of this structure that it spews out these elements. For me, guys, absolutely what you are seeing here on this screen is 100% categorical proof that cavitation in any place that it occurs has the potential to synthesize new elements, nascent elements. And as I've argued, even in my 2019 poster presentation, in reference to what was observed on the vibration system of Dr. Roy Shinamaza, and referring to our Ultra experiment, this is the way nature, I believe, creates bioavailable elements, and that is why I think living life likes to live near the coast waters, or near fast-running streams, or near springs, or near hydrothermal vents, because it's literally it's synthesizing new matter. And what you're seeing on here is utterly conclusive in my mind. Utterly conclusive. And it's not a one-off. This is why I kept looking. But of course, I didn't notice this guy down here when I first looked at it. But anyway, so what are we getting in there? We are getting, in this particular ejector here, obviously, by, I think that's by mass, yeah, by atom percent, 70.54% is carbon atoms. I'm going to zoom into that so you can get a better look. By atom percent, 70.45% is carbon atoms, 24.57% is oxygen atoms, and then you start getting the fusion of isotopes of these two into aluminium, and obviously carbon oxygen fuses to silicon, so you get quite a lot of that, and then lesser elements here through to copper. So this is the first exposure I have to what's going on here, and that was from this area here, And do I have another look at it? No, I go on to something else. Anyway, so this is the first of many examples that you are going to see of the proof of transmutation in cavitation system. I don't care. I really honestly do not care if Nature Scientific Reports pulls that paper. In my view, it would be an abominable travesty of scientific integrity for them to do that. Absolutely abominable. By the data that I have shared, which Bingjun Wang has more samples, and potentially any lab in the world that would want to verify this could do this with ease. They would just have to look at the telescope. It'd be Galileo, look down the telescope, see what you're seeing. Is this telling a story? And I think it's telling a very, very detailed and precise story. So let's go on. So in this case, it gets a little bit more interesting because we have two structures. Were they part of a larger structure? I don't know. But they're back to back, it would seem, because this one has its, let's say, inflow here, and this one has its inflow here, let's say. Thank you, Stephen, for your terminology there. And it has two tori in here, two half tori in this omega thing. And so was this the magnetic core, the phase singularity of these two structures? Okay, their collective moment. Well, let's see what we have in there. I'm going into that so you can clearly see we have this omega, it's blended in the middle. What are these materials that are here in this kind of omega thing going on there? What are they seeing here? So I look at it. Oh my God, look at that. We have here in this area here, okay, this part of this sample here, this large chunk here, we have, what is it? Silver. Every single silver peak there, and we are looking at 60.68% silver by mass concentration. This is not the first time we have seen silver. We saw silver in the cavitation system using nickel and potassium carbonate with ultrasound in 2017 in Suhas Ralkar's lab. And it was a toroidal type structure, and in fact it was basically almost 100% silver. We have seen silver in the Amasa gas on calcium carbonate, and if you recall, it had those concentric wavelets coming out exactly as presented in Solin's Mikhail Solin's 1992 patent, and on the ridges we observed silver. That was independently analyzed by SciTech. I wasn't there for the analysis, and they found silver. We have synthesized silver in a 300-second ultra experiment, although at a low ratio. It's not the only experiments that appear to have been synthesizing silver. There are several others. In fact, I'm going to quickly look because I have a directory here where I actually did a presentation called Making Silver. So, and one of the in that presentation, I looked at this, which was the ejector from what would appear to be a white hole or a black hole, and on this strand, this is on a Hutchison sample, it progressively goes to silver, and then it progressively goes away from silver as the compression in this string is effectuated. This was the one that produced this is nearly a pure lump of silver, or a high concentration of silver coming through the side of one of the peaks with a trough on a ultra experiment that we conducted using a $35 ultrasonic cleaner. And the interesting thing about this conglomeration of silver is blending into carbon, and it's punched itself a hole through the aluminium foil. So it's almost like the coherent matter came through. It got disrupted by being excited by going through the aluminium foil, and it basically shed its contents here in this silver blob. Yeah, so that is the analysis here, and you can see the silver content going up as it goes down the length of this fiber in the Hutchison sample. And what else have we got? I'm going to actually bring up the presentation of making silver, so I can show that to you. Okay, so here it is. Okay, so we looked at a bunch of stuff here, and we looked at the vortex systems here and the fact that it produces calcium and so on, and the different spheres and whatever. Okay, there is actually Solon's patent here. It's actually well to do to talk about and give credit to Solon at this point. Electron beam furnace, kinetic electrons accelerated at high voltage electric field, spontaneously proceeding low temperature nuclear processes with the excitation of self-sustaining controlled chain reactions of nuclear fusion, functioning under conditions of combining electromagnetic, gravitational, and nuclear interactions. This is unification of the forces in a massive nuclear fuel, generating directly in the nuclear fuel coherent radiation and superconducting currents of magnetically charged particles, obtaining a superconducting nuclear material and a nuclear fusion product with the chemical elements formed in the process. And he used as a fuel titanium, zirconium, niobium, hafnium, molybdenum, or tungsten, tantalum, or vanadium. And these are all paramagnetic with low vapor pressure at the melting point. Now he says, a superconducting nuclear condensate is a magnetic liquid metal nuclear fuel that generates energy with the generation of coherent radiation under conditions of nuclear phase transformations in the mass of the initial product and the combination of electromagnetic, gravitational, and nuclear interactions in it. Synthesis of elements from helium to iron and other heavier elements, in particular carbon, nitrogen, oxygen, potassium, calcium, sodium, aluminium, magnesium, silicon, and iron. Those are what you are going to see, my friends, in the synthesis areas, precisely co-located with the things that are doing the synthesis in the work of Bin Huang, as we have analyzed this week. Okay, so the same kind of observations were observed by Urutskiev in exploding metal foil. He had a ball lightning produced. The ball lightning broke up into microball lightning and so on. Same elements produced. And here we go, Simon Brink. Same kind of elements produced in his. Now, this is what I'm talking about. This is the calcium. This is the before calcium, which is CaCO3. That's all you get in there. This was, as I said, analyzed by Cytec. I wasn't present for this. And this is the quantum coherent nuclear effect that's going on. And on there, we are seeing the production of silver, 7.8%. And it's at this point on point 12 on the crest of this coherent matter wave. Okay, and here is the silver that was observed by Suhas Ralkar. You can see the toroidal structure here and the vortex type structure on there. And it's again like the one that we produced in our ultrasonic experiment using aluminium. This is an ultrasonic experiment using nickel. Okay, and you can see the silver here in this is 94.5%. This was the device that produced it. This was the foil it was observed on. Okay, and here in the ECHO experiment, a separate experiment, you can see that he observed the production of palladium in this case. But anyway, you can see how all these things are related. Now, in the ultra experiment, on one side, remember, we have aluminium minus oxygen leaves boron. There's some boron crystals in there, and this is all related to the magnetohydrodynamic structure, and you're going to see this. You're going to see this today in the work of Bin Huang. Okay, you can see it's not massive, but it is definitely there by weight percent, 0.81% in this area over wherever it's over here on this side. Okay. So I talk about how that you can get the synthesis from different elements to silver. Okay, so there we go. Right. All right. So I will bring up the images again. So we have seen this in a broad range of systems. It is not a new finding, but it is very interesting in this case because it is so precisely co-located in the center of a much larger structure. And these two were probably acting together to create the moment that led to the production of this. And of course, on one side, on the yin, you get some selection of elements, and on the other, you get the heavier elements. This is the lighter elements, this is the heavier elements. It might be the case that these elements in this blob came from the destruction of copper, and that on this side, the heavier elements came from the addition to copper of matter to lead to silicon. The other interesting thing is this blob in the middle. What is that blob? That would probably be at the maximum point of magnetic pressure. What is that blob? Well, let's find out. Okay, so I actually do an analysis here on this blob. It's blob number 99. Okay, so then we just looked at 101, but what is blob number 99? Okay, let's go and have a look at 99. 99 is... 98 is... Where's 98? What's 98? 98. 98 is up here. This actual strand here that comes into the vortex of this, or maybe coming out of the vortex of this, that strand here is what? It is iron. Iron. Okay? So there's the symbol signature on the iron, and these are the other elements, and so on. You can have a look at this. This is a map that I did of this area, and so you can see how the different elements are located. The silver is clearly over on one side. Yep. Clearly over on one side, and you've also got silicon in this chunk here and this chunk here, or sorry, this chunk here, and you've got potassium here in this chunk, and so it's potassium and copper more over there. But anyway, the silver is very, very clearly demarked in this side of the structure. Okay. This is mostly carbon, actually, on this side. Okay. Right, next one. Now I'm kind of seeing what I'm looking for. I start looking at this, and of course, the fragments on this one have got silver in them as well. So there was some particularly fruity ones going on. There's also some, it would appear, some small amount of zinc in there as well, which is a proton on from copper. But yeah, several of these sample points have got by mass concentration 15, 41, 13, 42% silver. So I'm looking at a bunch of these structures. So, as I said, this is not a new finding. Okay, this is not a new finding. We've observed this in several systems before, and specifically in structures identified by Solin. And I think this is just another icing on the cake of understanding how LENR works. Okay. All right, so in this particular structure, I found rather fascinating because it's another ball which looks like it's crashed in, and it has this comet trail. This comet trail, the same kind of comet trail that has been observed by Arutskiev, and the comet trail that's observed by Ken Shoulders and other parties. Okay. Like Winston Bostic. So let's have a look at that. Have we got that? Yes, so we're having a look at the comet trail here, and the thing at the head here. What do we have? Well, maybe we can look into that. Is it going to update that? Right, so we want to look at the head of that is 112, this little sphere is 111, and this chunk at the back here is 110. So 110, it was basically 110 to 113. What have we got there? What have we got there? 110 to 113 are down here. Okay, so some of the particles are silver and some of the particles are copper here. This one here, 107, where is that? 107, actually that's somewhere over here in this debris chunk over here. There's something that crashed in here. There's a lighter disc here and another disc here with some other material around it. Okay. So this might be the guts from another system which is completely different from this one. But anyway, so we've got multiple different locations producing silver. On the video, you will see where these are physically located to each other. And Thank you again. We've got up to 190. This is by far the highest number of people we've had watching a stream. Thank you very much. Great to have you here, Phil Dubois, to join us. And thank you. We have the head of the Cosmic Summit here. So George, thank you for joining us. And we also have Fom as well. So he probably introduced himself to you as Malcolm. Now, this is fascinating because of two reasons. We have this very bright spot here. And over here on this side, we have this very dark triangle, okay? So I looked at this and it actually showed something that was very weird. And I have not got an explanation from it, to be perfectly honest. But the first up one is sample 114, which is this bright spot. And what is it? Oh, it's our good friend silver by concentration 45.96, copper, interestingly, 15.73. It's also got iron in it. The idea that you've got a blended material containing iron, copper, and silver, well, that's quite interesting. But it also has carbon, oxygen, silicon, phosphorus, and sulfur. Okay, that is all going on in this sample here. But this sample here, this 115, 116 maybe, it has very high concentrations of copper. But the bizarre thing is that it's black. It's really black. And that would kind of imply to me that the backscatter electrons are not being backscattered. They are being captured. That is to say that this is acting a bit like a black hole. We're firing the electrons in and we're not getting the electrons backscattered. Okay? We are getting photons emitted from there that are seen as copper. Okay? So it implies that there's copper potentially underneath this structure, or on top of it, maybe deposited it when it died, but the electrons that we're firing at this structure are being consumed. I would love to have the time to spend and look to see if there are other examples of where on the pole of one of these structures, it is literally eating electrons. It's literally eating electrons. That's a very provisional statement, but it's the best I can come up with. I'm very keen to understand if there is anything else that could explain almost 92% copper. Yeah, when this is copper and carbon and oxygen and phosphorus. So all of this material is copper, carbon, oxygen and phosphorus, and this is all copper and oxygen, right? With carbon. Okay, this has just got extra phosphorus in it. But what is causing the electrons to be consumed here rather than being backscattered? Okay, don't know. Just don't know. Okay. So this is a broad scale area here. This is another one. I'm just looking around for different examples here. So they are very, very regular form. Okay. This looks like one's crashed into the surface, and then these ones here, they look like they've partially broken up. This one looks in a really bad way, but this one over here, I think we did look at that one. So let's see if we looked at that one. Okay. Yes, we looked at that one here. And what did we find? Let's have a look. This is sample 0.125. Sample 0.125. Oh, look at that. In sample 0.125, did we look at it there? No, there. That is, what part is that? It's this lump here, this little torus here, this kind of split torus here. What is that? And that turns out to be 24.19% silver, bursting out of the inside of this structure. Bursting out of the inside of this structure. One might readily assume that this is carbon. This might also be silver or iron, but this half ring or most of a ring structure, very similar to the one that we saw a little bit more close up in the other sample, the other object. This is coming out of this structure. Okay. All right. Now we get to look. I start at this point. I think, have I got to? No, no, okay. At this point, I start to realize that there are these objects where the guts are coming out of them. And I just take a whole bunch of these with these fragments stuck to the poles or being spewed out of the structure. Again, this one's been breached at this point, and the material is flowing out. This material, which is all of the elements you need for life, but typically also the elements that are formed in the crust, but coming from it would seem copper and water. Okay, look at this little beauty here. Look at this little beauty. It's literally like a little comet. We have our semi-deflated structure here, and it's spewed out this comet tail of these filaments of this material here. And again, there's some more of that kind of thing going on down here. And so, all right, it's at this point. Well, I'm gonna look at this, and then we'll talk about the next boom, which is nearly imminent. Okay, right. So, okay. So in the first sample point here, well, basically the sample points here show production of not necessarily everywhere the same, but you've got carbon, nitrogen, oxygen, fluorine, potassium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, and iron, with copper in every single sample point. Okay, so this shows to me that we have synthesized material. And I think the signature of this synthesized material is it's this like gray kind of homogeneous blob. And the idea that you can get material as contamination that has both organic and inorganic material in a kind of glassy blob and emitted from, you know, one of these structures, it's kind of a little bit tenuous to kind of believe that it's not actually coming from the structure. Right, okay. So this next image here I took because I really liked it, because it showed 3 different examples. This one with something bright going into the pole, this one with this dark blobby mass coming out, and this one with nothing but the vortex. And I'll show you the analysis here first. The analysis here first is that, very quickly, on this one up here, it's 133, I think. This one is 132, and I didn't look at that. So 132 is the dark one, and that has, by mass concentration, 38% carbon, 39% by mass, and this means most of the atoms are actually these things. But spewing out of this one here, we have iron, and also silicon, and also aluminium, magnesium, and potassium. Very, very clear peaks. Look, these are indisputably the elements that are contained within this ejector. I believe that this is material coming out of this structure, okay? Coming out of. This probably would be the input part of the vortex, and it's just sucked one of its little brothers in there, or this is a vol-au-vent slash one of these Oreos, fat Oreos coming out of the structure. But whatever, this is, in my view, synthesized material that was synthesized in there, and it's just kind of like farted it out, whatever. Over here, what have we got here? Well, on this one, we have 61% copper, 62% copper by mass. In that case, I believe that this is literally torn from the copper pipe. You can see it almost has a little bit of a helical nature going in there, and this is eating this for breakfast. It's eating this matter that this beam, this disruption beam that's come out of this fractal toroidal structure, is consuming this material coming in. Did these come out of there? I don't know, but we're going to have a look at that. And this one, which I don't look at the flow pattern coming in here. And so I had this in my head, and in fact, I did some close-ups of these. So here we can see the close-up, and here we can see the close-up, and here we can see the close-up. And I did this in my head. I thought, oh my God, you are kidding me. You are absolutely kidding me. I'm going to show you what I'm going to show you next. I need to load up Photoshop. Okay, so give me a second. I need to load up a couple of PSDs into Photoshop. Right. Which ones do I want to do? There's that one, and that one. Okay, we'll do that one. Right, good. Okay, we'll come back to that. Right. Are you ready? Are you ready? Okay. All right, it's going to be fun. Here we go. When I looked at this, and then I went to bed, and I thought to myself, they've all got this particular aspect ratio. It couldn't be. It couldn't be. And then I thought, it probably is. So thank you to Tony Giboni for this particular model, but I only overlaid, as I said earlier, the 2D geometry. It's not at the angle. So for instance, this is not, it's actually tilting towards the bottom right here, but you'll get it. 3, 2, 1, boom! And it's on the wrong slide. We misfired there. Let me hold the right slide here. Let me just check I'm doing this right. Nah. I'm going to put the hold music on here. Dum, dum. Okay, let's just check I've got the right one here. No, it keeps doing that. Why is it doing that? Well, we'll go like this. Right there. Right, go, and there. Okay, all right. I'm going to get it right now. Okay, you ready? 3, 2, 1, boom! Oh dear, can you see what it is yet? Can you see what it is yet? It is exactly and precisely the ratio of the sacred geometry. Let's turn it off. Let's turn it on. And you can see where the Sothic triangle comes out here. It's just shy. In fact, the center line of those feelers coming out. And it comes exactly down to the center of the mouth in the human anatomy. Okay? But of course, when this was wound up, this would be coming out a lot further. The tornado that comes out would be coming out a lot further. I predict that when I put the 3D geometry over this and correctly align it, the Sothic triangle will exactly match the type of line here. Of course, we do know, because this is a vortex nature and it winding around, that if the clustering under here is below the swastika, the 4 levels substructure inside here, then it will have it will spread out more and more and more in like a hyperboloid spiral type thing, or some type of spiral, rather than being a more focused tornadic beam. Okay. Now, what this shows us is that the inside, the core here, is the central tor, okay, and this is the apple, okay. So what they are doing with hot fusion is they're essentially trying to build stuff in this tokamak here, this tor in the middle, but we can see that it is influencing material all the way out to the apple. And we know for certain that if this is spun up to a high degree, it will end up influencing matter all the way out to the non-radiating boundary, beyond which there will be no influence whatsoever. None at all with ordinary matter. But what this implies is that a hot fusion tokamak reactor, wait for it, will never work. 100% certainly, because you cannot fight nature. If you get it doing what it wants to do, which is this quantum coherent nuclear process, it will self-organize with those diachron instabilities and those magnetic islands. And sooner or later, it will literally destroy the reactor. It's not a choice. It will just do it. Okay? So it's a fool's folly to be doing hot fusion, when you can just do sound in water and it'll also destroy your reactor. I'm joking, of course. You need to give it something to work with. Why pay I1? It will not necessarily melt. It'll literally disintegrate. It interacts with the way metals are able to form a metal bond. The electrons are changed, and so it will cause it to fail. It will cause it to fail. Right, so let me pull up the next image in these series. Okay, so here we have, oh, we do, and I'll show you. Here we have our second one. It's a different one, trust me, it's a different one, but also, how big is it? Well, if we look at the scale, notice the title's still wrong down here. The scale is 20 microns, and if I take that scale and invert it and overlay it, it's almost exactly 20 microns. And this is one of the stated quantization levels of Kenneth Radford shoulders. Absolutely spot on. Well done, Kenneth Radford shoulders. Congratulations. This is literally one of the quantization levels. And we have seen this in basic ultra experiments where it creates the yin-yang. And there is zero or very little effect outside here. For a lot of the cases. And you can see how precise this is and how the tornado tail is like bending off to one side, just as it is necessarily doing in the Great Pyramid of Egypt, that quantum coherent ether vortex generation system that we have in Egypt. Okay, so very, very precise. Could not make this more clear that that is the way it is. I've got one more example of this before I show you the next boom. You've got to be ready for the next boom. You've got to be ready for the next boom. It's coming. Right. Okay. Right, where are we? Ba-dum-bum-bum. We'll put the whole music on. The flux capacitor, which indeed this is. Okay. We're going to visit this particular one a little bit later because you'll notice it has a kind of smoother outside. So I believe there's a higher level of substructures inside here. And what you will notice is, and the data points to it directly, this starts to become iron on the outside. Okay, starts to become iron on the outside. But you're ready for the boom? 3, 2, 1, boom! There it is. It's exactly the same structure. The implications of this are, and again you can see it's coming out in fact in this case you can see like 2 sections of the torus coming out, the vortex coming out of the center. It's got these 2 kind of like sections, and this is what we see on the ultra sonic or sound vibrated plates of Dr. Roy Shinamaza that we analysed with a twisting double helix coming out of the center. Okay, so there, boom, right. So this got me thinking. I was looking at our images, and I said we would come back to this. I said we would come back to this because once I'd cracked the code to the overall structure, I thought, okay, so that means if they're always regular and they're always these particular quantized states, then very necessarily these other things must be related to this. And about 20 minutes later, I said to myself, oh my God, Alan, the Oreos are the center of the hydrodynamic vortex. You ready? Are you ready? Is it going to let me do it? Have I got it? Are you ready? Not that one. This one. Can you see it yet? Can you see it? 3. Yeah, I'm on the right one. Yes. 3, 2, 1. Boom! They are Oreo shape because they meet in the middle. You get it? They are Oreo shape because they meet in the middle. They are in those structures. They are in those structures. Okay? Now, if they come out, they can start to become more Volavontish, but it's all over. And what this particular image here is telling us a beautiful story of the death of 3 of these structures. And what happens is you can see that they still have some relative moment left. So this one died. This one died in one orientation, and as this was spinning down, this one started to roll back round this way. Okay, it wanted to travel because this one was a little bit more dynamic than this one. This one died, and this one wanted to roll back round this way. So they are basically the same thing. This one, its pair did die, but it was more active than this one. And you know what? The center of the vortex here is left a hole. It's left a hole. Okay? This is, in my mind, utterly conclusive. Utterly conclusive that the substructures are these structures. Okay? Absolutely conclusive. We literally have a new method to simply create the most important elements for life. And let's have a look at the scale. The scale typically here, if we move this around a bit, from, well, actually it's this one we want to look at, from the center of the gyro. These are 2, 4, 6 and a bit microns. Well, Ken Shoulders said that typically the smaller ones were about 5 microns, so that's within a stone's throw of what Ken Shoulders said. Okay? So this is wheels within wheels within wheels. And you will see in these samples there are even smaller wheels. Can you see it? Can you see it? There's a little Oreo here. There's a little Oreo here. Wheels within wheels within wheels. And the other thing is, I didn't realize at the point when I was looking at this, out of this one, it's got this carbonaceous type ejector. Carbonaceous type ejector. So these are able to do what the bigger one is able to do. Maybe these ones, and it's all a case of how much does it spin up. Now, if I align a couple of these, can I do a range 4 up? Can I do 4 up? Oh no, it's gone down there. Right, okay. I'll pull this up there then if you're going to do it like that. Okay. I'll put these all to the same. Well, let's put it to 33%. Why not? We'll put this all to 33%. Where are we? Oh, I can't see the bottom there. That's not very helpful. Let me do that again. Window, range 4 up. We'll go full screen here. That'll help me. We'll go 33 here. Right. These are all exactly at the same magnification. These are all at. Okay. So. Essentially, sorry, that's at 4,000 times multiplication, so that's no good. So let's do this one. This is at 5,000 multiplication and 20 microns, 5,000. So these are all the same size. So if I put this at maybe 100%, is it going to get on screen? Yeah, okay. And we'll put this one at 100%. Okay. So they are essentially what I did here. In fact, I'll put that at 75%. What I did here is I aligned this structure on here, and this is 5,000 times 20 microns. So this is exactly the same scale as this. And all I did was I dragged this version of the sacred geometry over this, and these internal parts exactly and precisely lined up with these Oreos. I didn't do any changes other than rotate it. Okay? In fact, I'm going to do it here right now. Let's do that so you can see. These are both at the same scale, same magnification. I'm going to rotate that round so you can see nature gets this right. There is no way you can improve upon what nature is doing here. It's utterly, utterly exact. Okay? Utterly exact. I've just done it again. Look, there was the original one. Here's my new one. I'm not rotated it as precisely, but anyway, you get the idea. Okay? Absolutely precise. Nature does this precisely. Okay? Alrighty then. Wheels within wheels within wheels. We will get back to our data. How is everyone? 181 viewers. Thank you very much, guys, for spreading the word. That's fantastic. Let's go back into the rich data that we have to share today. And we need to catch up with where we were, which was, what were we looking at last? We were looking at, yes, we were looking at the ejector here. Okay, so it gets even more beautiful in a minute. So here is our, no, it is if I'm definitely showing the right thing. Right, here is our 3 structures. The one that's spewing out synthesized elements, the one that's capturing the raw material to synthesize elements. And look, it's just like a tornado. You've got stuff on the outside going up, and maybe this is coming down. I don't know, but it's got a Paisley type shape. here in this bit that's coming down. And I think basically on samples from Benjuan Huang of these collapsed pipes, literally every single aspect of how this force of nature, this formidable force of nature works, can be defined in excruciating detail. But anyway, I think you get the most of it here. So this beautiful little one here, where maybe it's a little substructure bleeding out the top. This one here with the substructure here and a substructure here, and again this becomes more like a vol au vent it's come out of its this confinement inside the structure. Okay, and then this is the one showing the Sothic triangle coming in here. Okay, look at this little beauty here. Look at this little beauty here. This is orthogonally arranged to tores of tores of tores, etc. This is literally going into the core of this, and this one's literally going into the core of that. It's absolutely mind-bending, and it's so precise. This, for me, is one of my favorite images of this image set. I think it's a seminal image, and you can imagine that all of this material is going through a point that is infinitesimally small. So all of that matter somehow is going through something that's infinitesimally small at the center of this structure, and vice versa with this. Okay. What an honor it has been to look at this sample. Thank you to all of the sponsors out there that made it possible. Most especially, thank you to Alan Goldwater for buying the SEM, which didn't work, and he spent $70,000 on it and spent another $30,000 getting it working, so that the project could use it this week and in previous years. And thank you to Benjuan Huang for having the courage to reach out to me and for agreeing to give me a sample to look at. But I can guarantee you that if other people get these kind of samples, they're going to see this kind of evidence, which is utterly conclusive. Utterly conclusive. Okay, we're going to have a look at some other ones. No, sorry, I just want to go back to that one. Just dwell on it for a bit. I actually did a contrast-adjusted version of this, which I'll have down the bottom here. Have I? There, this one? Yeah, there you go. I contrast adjusted it there. Most of them are just raw off the SEM. And I contrast adjusted this one, which we'll come to in a minute. Whoa, it's so exciting. Where are we? Okay. And now we start to get down into the substructures of substructures. And I actually haven't even done these things in Photoshop yet, but I'm going to do them live with you. This is on the title slide for the presentation. And this shows in extreme detail what is going on here in this process. What do I mean? I mean that this, you can see it's got a kind of hexagonal structure to it, just like we saw in Matsumoto's work, just like we saw in some of our other work, and just like you see on the inside of the outside and the outside of the inside of the 24-inch thunderstorm generator. This is the vortical structure, but we know this isn't spewing out stuff from the top. It's going round, and the tornado comes down, the kind of monopole disruption beam comes down from the bottom. And what's happened is, if you can imagine it, you've had your sphere, and it's coming in like this, and there's our surface of the copper, and the tornado is coming down here, and what it's done is the tornado is starting to suck up material, but as it's doing it, it's sucking itself onto the copper, and it's crashed into it. And that is what it's showing here. The engagement of the tornado reached down from wherever it was in this flow and hit and engaged with the copper here, stripping increasingly wide strip of material until it connected with the surface. Boom! absolutely mind-boggling levels of certainty with the way this is working. It's telling you exactly what is going on here. Okay, but looky here. What are these? Well, I think we know what they are, because where do we see them? We see them in the top of our Oreos. I'm going to go and find an Oreo now. Where's my Oreos? Not there, not there, not there. Let's find it. Let's find a good collection of Oreos. No. Well, anyway. Somewhere. Okay. So here, look. Look at the top of this Oreo. It has these triangular pieces here. And we already know that the maximum synthesis will occur either going into or desynthesis or coming out of one or other of the side of this. But you're going to see a little bit more of that. But what I'm going to do is right now live, and I actually don't know whether this is going to work. So this is just what it is. I'm going to try it because I wanted to try it, but I haven't had time. So I'm going to do it now. This, right? We're going to take this into Photoshop. And I suspect that one of the internal structures of the magnetohydrodynamic structure is this. And I think what happened is two Oreos perfectly came down in their pair and then bounced off again, and they left a bit of their material on the surface here. I don't know whether this is going to work, so it's a bit of a risk, but let's try it. Why not? So we're on 30. I need a 30 micron one. 30, okay, and which one is it? That one? No. No, that one? No. I'm going to put the whole music on. Talk amongst yourselves. The Flux Capacitor. And it's obviously the last one you try, isn't it? Always. Okay. Oh, that isn't even 30 anyway. Where's the 30 one? Oh, God. Oh, well, that doesn't work. Okay. And we want to open this in Photoshop. Yep. And then we go like this one. Yeah, okay. Is everyone there? Don't know whether you're there. Anyway. La, la, la. Nearly done. So you'll get the idea, kind of what I'm trying to say. Yeah. Not overly convinced, but anyway. Such is life. So, there we go. So, what I'm saying is this material, which will have come out and become bigger matter, you can maybe see there is a sweep around here, sweep around here, sweep around here. It comes across there. So I think the overall central apple will be there, and approximately putting that in place, you can see there's a curve here and a curve kind of there. And is it convincing? I don't know, maybe. But that's what I'm showing you. maybe it's the other way around, the upside down, I don't know. But that's kind of what I'm suggesting, is that out of the top of the Oreos, this little set of florets comes out, and that's why they're there. Anyway, that was that. I just wanted to try that and thought I'd do it now. Okay, all right, let's go back to the rest here. Okay. Give me a second. Where's my source here? Okay. Right. This next one is very valuable in my view. So here we go. So it's crashing in, and normally these materials, these structures, they're very like lumpy with these like kind of planes in the kind of vortex. You can imagine this like it's like a big weather system, and this is the tornado or the eye of the hurricane or whatever, or the tornado reaching down. And it's quite lumpy. It's quite lumpy. You can see on those two. I don't know whether I've got any. Yeah, these are quite lumpy. You see how it's kind of like in layers and in lumps. And I imagine this is in the coherent matter wave. This is all kind of part of the wave function. The wave function immediately collapses, and this is the product of the synthesized elements that come out of it. Okay, but in this next shot, not this one, no, not this one either. It's coming up soon. Yeah, do I actually do an SEM on that? EDX rather? No, I don't. No, I don't. Okay. I'm just getting a bunch of other examples here. So you can see a whole bunch of examples. Okay, so this one here. I noticed that this one was smoother on the outside. And I thought, what's going on with that? Why is that one smoother? Okay, well, we're going to find out. Here we go. I'm looking here at sample point 134 for this bit up here, and 137 for the outside of this. Okay, and I've got another one. No, sorry. 135 is this bit. 134 is the outside, and there's another 137 here, which is the outside. Okay, so 134 and 137, notably smoother on the outside. Okay, same kind of aspect ratio, but notably smoother. Okay, so what are the outside of this? Well, nothing much interesting on that one, but look, our two 134, 135, 1.71, 17.6% iron. Boom! That is implying that as this fractal toroidal structure gets more and more intense, it will synthesize iron in the core, which we have been observing. We have been observing that some level of iron is produced in the internal structures of this from what they vomited out, which you're going to see a lot more of. Okay, but as it builds and it grows and it maintains its stability, then it starts to produce heavier elements, and this tends to produce iron, and the iron is now on the outside. It's on the outside, and it gets smoother and smoother. So you can see how it would progress from the light elements, the water, the oxygen, hydrogen, and maybe even using the heavier element of copper, and you're ending up with some iron being synthesized here. Okay, so I think I go to another session here. So that might be the end of that session. That might be the end of that session. Oh no, I actually do a map here. Yes, I do a map. And there we go. You can see there's a whole bunch of iron all the way. All these lumps here are iron. Where is it? Okay, and there is a little bit of iron on the outside, but most of the iron is actually on that top side. Okay. Also, aluminium is co-located in a couple of the chunks on the top here. So we've got aluminium and iron being synthesized in this little beauty. Okay. All right, so that's that, and we're going to go to another session. If anyone's got any questions at this point or any ideas, please put them in the chat, and I will go and get the next document. It's the end of the world as we know it. It's the end of the world as we know it. But I feel fine. Okie dokie. Righty. Let's move on. So, again, I'm starting up for a new session, new day. We're now on the 16th of this precious month of our year 2024. And I'm looking at a different area on our sample here. And we go in, and we go in, and we start to see one here. And I'm starting to realize these things get deflated and they spit out stuff. So I look at this, and nothing particularly interesting on the outside of that. But here, up here, if this spat out its two Oreos, and the one here is the stronger of the two, right? And this is the one that becomes a vol au vent as it kind of like expands out. What I saw here was this was spewing carbon out of its pole, but not the other side at all. Not even slightly. You can't see it. I'm going to move my face. Right, there we go. This Oreo here, so if I go back to the previous shot, so I'm speculating that this one died here, and out of its structure came these two. It's in the same direction. This is again the collision area where it sucked up the material and it spat these things out. And we've got the one as a vol au vent and the one as a fat Oreo. When we go into this and close up here, and I look at it in different technology here, nothing coming out of this side of the fat Oreo, but a plume of carbon. Now, the idea that Benjamin Huang, I'll say it here right now, again, if Nature scientific reports say they do not believe that Benjamin Huang's system is creating carbon, they need to look at this data. And if they still don't believe it can be producing carbon, ideally, those people that are decision makers, not the people that are told what to do, people that can make real decisions as to whether this is real science, they need to ask for a sample and look at it. And I guarantee you, they're going to find the same thing. Okay? It will be the biggest travesty in science, in my view, in my lifetime, if they find some way of attacking Benjamin Huang's paper. I'm just saying that because this is hard physical evidence. And nature doesn't lie, it cannot lie, and it hasn't got an agenda. Carbon is coming out of this structure. There's no, this isn't a blob of carbon that happened to be in this location and it was very, very lucky. No, it's coming out of this structure. And this is a self-similar structure to the bigger structures. In this case, it spewed its carbon down here, but it also spewed something else. And this looked very much like the other object we saw with a sphere at one end and material and something at this end, okay? This comet trail type deposit, okay? What is it? This is when you're looking at it under the SED, the secondary electron detector. So you actually get to see some geometry here. And you can see that this has a vortical nature to it. It's got this bit sweeping over here. If I had done the contrast adjustment, you could probably see that a little clearer. But there's a tornadic vortex going on here as it's going into this structure over here. Anyway, we're going to look at this, and what is it? Well, nothing too interesting on the first one and the second one, but we do a map here, okay? And yes, this is carbon in the pink coming out. This is all carbon. Now look at the this little line here. It's got a tornado in this bit here. So like I was saying, there's a tornado, but in the center line of the tornado, or rather on the outside, you can see that that actually has this tornado type structure, okay? But what I noticed was, look at the bottom here, this bit down here. These are large chunks of iron, okay? That were associated with this side, okay? Carbon plume coming out, carbon trail. Phosphorus on both of these structures in this beautiful copper oxygen landscape with this very, very clear iron coming out of this material, which was deposited by this structure. Okay? Phil says, iron booger. Yeah, about just right. It spat it out. I came up with all kinds of analogies for what we're seeing. But anyway, right, so we will move on. So you can see that. This is the next one. So I start looking, this one is broken up here. These might have been a pair, okay, in a larger structure. And is that all I have for that one? No, okay. Obviously, all of this data will be shared. And I will say, please credit the Martin Fleischman Memorial Project. This is a project that is community interest based, but share wide. And please credit Alan Goldwater and the Magic Sound Lab, because without his leap of faith in buying this SEM and the grief he went to go through to make it, this would have been possible. Okay. All righty. So I looked at this, and of course, what do we find in, what's this, sample point 154? Where is 154? 154 is here. It's on this lump on the periphery of this material going around in this structure. We have a sensible amount of iron. How much is it? It is, how much is it? It is 20%, 19.3% rather, by mass concentration. So you can see that these things do like to grab magnetic material, and it would appear that it's synthesized within these structures. So it's not surprising that we end up with iron-rich crenellated microspheres. Okay, right. What next? Here's a little structure. What do we got? So this will be one of these carbon films from Matsumoto, and in the outside there, in sample 157, we have all of the elements that you normally see: carbon, oxygen, fluorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, iron, and copper. Of course, it's got copper in there because probably that's the feedstock in this case. But the predominance of the mass, and by the vast majority of the elements, are carbon and oxygen. And there should be very little carbon in this system because it's basically water, deionized water. There shouldn't be any of these things because it's deionized water. And the partial pressure is extremely low of carbon dioxide. So the dissolved carbon dioxide naturally coming in from the deionized water would be extremely low because it's only 0.04% in the atmosphere. But you can see these peaks are not slight peaks. These are 100% bang-on peaks in this signal here. These are very, very clear and exact peaks in this homogeneous material. Look where it is. It's literally here. This basically one homogeneous material. How can you get a completely homogeneous material made up of typically biological and non-biological materials, typical elements? Okay. Here's a nice little twisted one. I don't know whether I do any analysis on that. Maybe, I don't know. Yes, I do. And it's just the usual stuff because it's a little one. This one has really spilt its guts over here. And I like this one because this structure's come out and it has 1, 2, 3, 4, 5, 6, 7, 8 or so, 9 maybe, very distinct substructures in something that's come out of this. So it's broken down and broken down again in this process. Do I look at that? Yes, I look at that, and it would appear it even has a little bit of zirconium. I'm not so convinced of that. I'd have to have a look at the products there, but it's got a lot of chlorine in there, but nothing too interested in that particular look. Right, now, I need to prepare you for the next thing. I have said that these structures will eat anything based on physically observing what they do to material. What you are going to see in the next couple of images is categorical proof that these things will vanquish anything, in my view. And it's still shocking knowing that it can do this, but to see this exact and precise evidence of what it can do. Are you ready for it? Are you ready for it? Okay. On this frame here, you can see whether a very large structure collided somewhere here, or maybe its tornado tail collided here, and it damaged this copper oxide, stripping it down to the copper. And one part went down here, and some sort of break up here and continued all the way down here. And another one ended here. There's two kind of streams that it ended, okay? What you're going to see is totally shocking. 3, 2, I'm going to take my mugshot out. 3, 2, 1. No, it's not done it. 3, 2, 1. Boom! I just want to let you look at this and let it sink in. What is this? Well, it is pure copper, pretty much, all the way around this. Pure copper. Look how thin it is. This is 20 microns, so that is 2 microns. So half of that would be 1 micron. This is maybe 100 nanometers. And it's in waves. What's happened here is that structure there. Look, that's that structure. And as it collided with this material here, it's literally stripped it. And it's wrapped it around like it's wrapped itself in apple peel. The strength of even just the little interaction of this boundary with the copper, it's able to strip on the outside of this, but you can see how thin this is. You can see how thin that is, right? So again, half of the little 2 notches here, the smaller ticks here, is 1 micron. So I would say that this is stripping maybe 200 nanometers or 100 nanometers of thickness. Okay? 100 nanometers of thickness. And look, it's in waves. 1, 2, 3, 4, 5, 6, 7, maybe 8. This is maybe 16. This could have 16 subdivisions in it. And it's also waves this way. You've got a long wave there, then you've got a scallop there and a scallop there. We've seen scalloping going on in other systems. We've seen sections taken out of line reactors. And I believe it's this kind of structure that's doing it. And it will vanquish anything if it comes within the this particular boundary of the apple. Nothing will be able to stop it. Nothing will be able to prevent it. Now, what else have we got in there? Well, look at the map. Look at the map. Down here, this is a chunk of iron. Yeah? See it? It's a big chunk of iron. Right? And I believe that this was synthesized in this overall in the overall structure of which this is one side. Okay? The other side went on a lot further down, all the way down here, all the way down here, all the way down here. I look at this area, I think, next. You can see where this damage occurred. I think I looked at a specific area here. I looked at the iron there. It's nearly 20% iron. I look at this. Nothing too special about this area. This is just an impact site. And I then look at this one. Okay, and I'm starting to recognize at this point, it's a learning process for me. I'm starting to recognize at this point that this is probably elements that are already there. This is the carbon coming out of the bottom side or maybe out of the Oreo. But this flake here is probably synthesized heavy element. I'm recognizing that now. It's becoming relatively easy for me. And when I do the map on this structure here, what do I see? Well, look at that. Iron. This is mostly iron. Okay? The rest of it is the usual stuff for these, but this little fleck associated with this structure is iron. And you can imagine how a big one would collect all of these pieces of synthesized iron and pull it in and wrap itself around with that iron, okay? And end up with lots of substructures in there, and you can see how you would get to the iron-rich crenellated microsphere, okay? And the material would end up being part of this vortex that's spinning around and producing this spherical object, okay? And inside you have all of this material that's synthesized and so forth, okay? So very high peak on the iron there, very precise, and also it has vanadium and chromium. Chromium could be coming from steel, but vanadium was observed in some of the other authors that I showed you earlier in the Making Silver presentation, so I believe that that is synthesized. And chromium we've seen in the ultrasonic experiment from Roy Shinamaza, where it had these vortexes in a double vortex, and in the center it had carbon. Further out from that it had magnesium, which is double carbon, and further out from that in this spiral galaxy it had chromium, and chromium is double magnesium, and magnesium is double carbon. Okay. All right. In a vortical pattern. So here we go. I'm looking specifically at this now, and it turns out you can see the vanadium in there. It's not a small amount, 3% by mass, and the iron is 9.3% by mass. Still, the majority of the structure, or the bulk of it, is either carbon or oxygen or the feedstock of copper. So you can see that this isn't just a lump of iron. This is a homogeneous blob that additionally has vanadium, iron, aluminium, silicon, phosphorus, sulfur, and so on. Yeah. Okay, and I do a close-up on the map here, so you can see that very clearly. And there we go. The aluminium is co-located with the iron. Aluminium is co-located with the iron. And why is that interesting? Well, if you double aluminium, you get iron. 2 aluminiums makes iron. Okay? So very, very clear data here. And then I see this very bright spot actually here where the vanadium is. And I go and look at that specifically here and look at the spot there, and that's the spot that you can see. Very, very clear peaks for the vanadium. It's definitely there. It's not guesswork. It's definitely there, right? In combination with copper and iron, but all these other elements, the aluminium and silicon and so on. Okay. Right. That is that one. So we're nearly there. We are. Yeah. So Ret Oracle says subatomic restructuring. Yes, that's exactly what it is. So let me put the still up, and I'll get the last of the Word documents. Okay. So here we go. This is the last of the Word documents for the evening and or day or whatever, wherever it is you are in the world or whenever you're watching this. You can see the material coming out of or going into here with the cone coming there. You can see the cone's influence chopping this off, coming into this one. So it's a beautiful thing, this precise sacred geometry. This is not approximate. It does the same thing every time. So I'm just taking a whole bunch of stuff now as a resource. This one is very much buried into the surface. Again, I don't even bother looking at this one because you can pretty much tell what it is. Or maybe I do look at that one. I don't know. So that's yeah, very, very tight fat Oreos here. With this one's got five flower petals on the top of this. So you can probably get an idea of what the substructure is in that one. And here you've got these things coming out. Maybe I have these somewhere. I think I did do these. Did I? No, okay. Right, this one really fascinated me because this looks like a breakdown of a structure. You've got a substructure of a substructure of the big structure here. But this one, I thought, I'll kind of see what that is. That looks like it might be the inside of the Oreo. Okay, and I start to see these disc-like but polygonal type discs around. And I thought, I wonder if that is. It couldn't be, because I'm starting to recognize the form of the synthesized material is this more homogeneous material here. Are you ready for it? Are you ready for it? Boom! That is a toroid of iron. Look, it's a geometric structure. 1, 2, 3, 4, 5, 6 structure of iron. And I believe that was synthesized inside the substructure of this overall structure here. And the rest of the material went away. But you've got to bear in mind this is like a phase change. It's a coherent matter that comes into normal matter. And this is just, for me, this is totally... I couldn't have expected the data to come in anything better in the order. You know, like each step was revealing the next level of certainty. And in part, that's because I've been holding these images in my head, and I've been lucky enough to do 3D for a good proportion of my career. So I'm able to rotate these things and see their relevance. But the fact that each layer revealed itself one after the other was, frankly, just an honor and a bit weird, to be honest, a little bit weird. But anyway, I'm not complaining. So yeah, there's a close-up on that, which we took the EDX there, and it's absolutely clear that is iron, no shadow of a doubt. And then we go and have a look at another one here, and we look at some structures down here. Not so special on that one. This one I rather liked because it was just cute. But I think it's just a fragment that's left over. It didn't have anything interesting. Now, this one, oh, well, there's a whole bunch of them here. And I think what you'll find is this disc here may be iron, and it's like a split Oreo. So I think possibly in the central plane of an Oreo, maybe in this central plane, there might be some iron. I don't know, and I think that's might be what ends up being flakes on these iron-rich crenellated microspheres. And if it's really powerful, the crystal-like structures that sometimes get produced, they end up being the bound-on like crenellations and stuff. So, and I think we will know that the reason they're just over a micron in size is because that is the size that it gets synthesized in the substructures at lower levels. So the first fractal structure that's able to produce iron produces iron of very specific sizes, and that's what goes and gets accreted onto the outside of these very big structures, which ultimately leads to the iron-rich crenellated microsphere. Okay. So there's lots and lots of examples here. We've got the big structures here, we've got the medium structures here, and we've got the little structures here. So lots of examples. But I liked the idea of this one because this looked like one has smashed and blown up. I'll go into it. It's blown up and it's left its toroidal core of synthesized material. It's blown up and left the toroidal core of synthesized material. Moreover, it has this incredibly bright spot here. And I thought, what on earth is that? Is this like some bit that came out of the center of this otherwise synthesized material at one of the subfractal levels? Don't know, but we investigated it. And what did we find? Well, we did 2 samples on that. No, we did in the central bit, we have sample 210 and 209. What are they? Sample 210 is here, and 209 is there. And what do they have? They have iron in them. In fact, most of these have iron. Now, what is this one? This one has molybdenum and tungsten. Molybdenum and tungsten. This light patch here, this one here, this bright patch here, is molybdenum and tungsten. But it's not on its own. It's mixed in with the copper, the iron, the chromium, the vanadium, the titanium, the calcium, the potassium, the phosphorus, the oxygen, and the carbon. Tungsten is actually, you know, it's the, how should we put it? It's the highest melting point element there is. It would imply that this is not melting going on here. It's coherent matter phenomena. But synthesizing these incredibly hard materials is beyond belief. Tungsten and molybdenum. These are classic refractory materials. And they are even fuels in the reactor of Mikhail Solin, his quantum coherent nuclear reactor that is clearly based on the principles laid out by the data that you can see here from Bin Juan Huang's Capacitor. Absolutely mind-bending. Okay, so I'm looking, what else am I looking at here? I'm looking at 207 and 208. These are the 2 flakes, and each of these 4 flakes, if you can look at this, each of these 4 flakes have a lighter material in the center. Okay, so I look at 2 of the flakes. I look at the outside of one flake, and I look at the inside of one flake. And so the inside is 207, the outside is 208. What do we see? We see 207 has 38% copper and 27% iron, and the outside has 35%. So the copper's gone down and the iron's gone up. This would imply to me that potentially the copper is part of the fuel in this particular reactor. Okay. Okay. Right. Next. Oh, well, okay, so there's a whole bunch of stuff going on here, another broken up structure, and typically we're getting all these different elements synthesized, lots of those. I put all the data there. So in this case, it's not tantalum. Don't ignore that. It's not tantalum. It's just a beamline inconsistency. Here, this one's really broken up. I like this because it has a disc down the bottom. Unfortunately, I didn't look at this disc, but I think probably this might have been iron. If you can see, it's kind of like that, polygonal substructure that's come out. It's clearly broken up. There's another blob over here that definitely looks like the type of synthesized material. Obviously, this looks like the synthesized material, and this vortex of material here definitely looks like a synthesized material. So what are we interested in? I looked at the vortex here, 217, this little bit coming out of this part of it, 214, this one 21 something over here, and this one 216. Okay, so what do we have? Well, in all of those samples, particularly in 217, which one's 217? 217 is up here. This homogeneous blob here has the highest concentration of iron by mass concentration 6.85%. But similarly, that material has carbon, oxygen, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, and titanium in there, right? This is coming out of the broken down magnetohydrodynamic structure, this flux capacitor that nature can naturally and easily build given the right circumstances in a cavitation hydrodynamic flow-based system, and it is synthesizing titanium and iron and all of the elements you need for life. Here's another one, and I like the one here because it actually has the beautiful shape of the dome going on. It's really nice to see the kind of overall influence field there, as this one particularly died. I don't know whether I looked at this one. Maybe I did, maybe I didn't. I don't know. No, I think I did an area on this bit where the iron was in this previous one here. And look at the certainty of the peaks here. Definitely copper, definitely iron, definitely titanium. It's not such a high concentration. I'm looking at a large area there, but potassium, calcium, chlorine, sulfur, phosphorus, these elements are definitely being synthesized by the process. This is, bearing in mind, this is a deionized water in a copper system, and that's basically it. Right. What have we got here? We look at something else here. Yeah, we look at this. There's another bright spot on there. And again, it's this tungsten, iron, chromium, vanadium. This is a different one. So again, another system has produced this. And the light spots are only on these fragments that come out of these devices. It's not like it's everywhere. This one I thought was quite interesting because these ones have obviously buried themselves so deep into the copper oxide. And then they've had a kind of deposit go on the top. I investigated that with the line scan. It's more of the same, to be honest. And with the line scan, you can see the interesting thing was after I'd done it, it ended up by removing some of the carbon deposit on there, which had some potassium in it or something. Anyway, the next one for me is a boom. I really enjoyed it. It was also part of the title slide for this. It's the one that you can see here on the right, and I will share with you that now and the analysis of that, and that is this one. Boom! Absolutely clearly coming out of this deflating structure, all of this material, okay? And you can see by putting on a bit of SED, this is a vortex structure, okay? It's like a big tornado. And the interesting thing is that this layered down over the top of this one. It's actually on top. So, like, this came into being ordinary matter and deposited it on this as this was coming in to crash here, maybe. I don't know. I kind of imagine it sometimes it might be like a balloon that's popped and it's just spewing out the air. But in this case, it's a load of synthesized matter. It's absolutely beautiful. So there is the backscatter electrons, which show you very certainly that this is copper oxide, this is copper oxygen with phosphorus, and both of them have got a bit varying amounts of carbon in, but this is ejecting this synthesized material from its internal volume and spewing it out. And what do we have? Well, we have in our first point of observation 221, 222, 223, 224. So the first point of observation, this is what? Which one is this one? Doesn't say. Okay. Is that all of them? That's all of them. Anyway, it's got iron, okay, in all but one. So 224 doesn't have iron in it. Which one's that? Interestingly, so this one doesn't have iron, but all of the rest of them have iron in, synthesized in this structure. Potassium, chlorine, and sulfur. Sulfur obviously is a fusion of two oxygens, classic fusion in Lena. And there we go. These elements here, iron, iron, and so forth. Stronger peak in iron there. Then I look at another one. This one. This is totally broken up, and it has literally a vortex sheath. Now, somehow all of that fitted inside this structure. So it must be under some extreme magnetic confinement. Extreme magnetic confinement. And look at it. That is the roll of material that's spewed out of this structure as it's blown up. What do we have? Well, we have all of the elements that we expect in these systems. I've done a large sample here of this material. Okay. 225. And what do we have? We have carbon, oxygen, sulfur, magnesium, aluminium, silicon, phosphorus, chlorine, potassium, calcium, iron, and of course, it's got copper in this material because I believe that the copper in this case is the food. Okay? Spin isotopes. Spin isotopes. 63, 65. Spin isotopes can be pulled in. That is why fluorine is a very good fuel. And I have said that potassium fluoride, I believe, would be a very good additive into these systems for cavitation. Okay? Potassium fluoride. Okay, so, right, let's go back. That's that one. And we have another one with its guts spilling out. Did I have a look at that one? Yes, I did. What do we see? We see all of the elements. Okay. Again. And this is interesting because in this one we see potassium, carbon, oxygen, sodium, right? Good strong peak of sodium, fluorine, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, cadmium, potassium, calcium, iron, copper. So the new ones on the block here are sodium, cadmium, and a stronger peak on fluorine here. And it's not a nothing, you know, it's actually 1.3%, 1.38% by mass of cadmium. This is a very heavy element. Okay. So someone asks, Paul Shields, how do isotopic analysis of these small samples? Well, you can do, if we gain access to it, time of flight sims, so TOF sims. You hit it with a high strength beam, secondary ion mass spectrometry. So you can hit it with a beam of high energy atoms and it kicks off the atoms, and then you look at the time of flight for the atoms that are synthesized. So this particular sample could be suitable for that. So we can look around and we can find out what the syntheses are. But because I believe and have said very many times that this is the way nature creates all of these elements, and we're seeing now elements like tungsten and molybdenum and cadmium. These are not light elements. These are not light elements. So this can produce all of the elements in the periodic table, and depending on the resonance involved, there will be larger amounts produced in certain systems than other systems. Okay? All right. So there we go. So, you know, if I was to spend more time, I would just spend more time looking at the exploded guts, the fart bombs that come out of these device, these little structures. So here's another one, and I rather like this one. I couldn't decide whether it was coming out of this big structure or it's coming out of this, but maybe it's coming out of both. Maybe this is the vol au vent, and maybe I've got, yeah, so maybe this is the vol au vent that came out of this big structure, and it's spewing the stuff out as it's coming out, okay? And so I actually go in and look at that closer, right? What have we got in this one? I look at it here, so we are going to look at 3 areas here. We're going to look at the immediate out area here, out there, that area, that's 230. They're going to look at the gap in the middle of here, the gap in the middle, and then that is 233, 231, or then 232 here. What have we got? What have we got? We have got all of the elements. All of the elements: carbon, nitrogen, oxygen, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, iron, and copper. Are you getting it yet? Are you getting it yet? These flux capacitors use their magnetic strength to suck in via their tornado both themselves and other matter. And inside their structure, they are cohering that matter and producing vast amounts of nuclear transmutations. And then they are spitting out the product when they die. They are literally like living creatures. Okay, so what else? Yeah, like all of the elements in this gubbins going on here. They're all there in beautiful detail at very high sulfur peak here. Of course, it's still mostly carbon, nitrogen, oxygen here, and we're seeing nitrogen coming in here as well, which shows that Malcolm Bendel's system, I predict, is producing nitrogen, and we are seeing nitrogen synthesis here. Now, there should be some nitrogen in there because it's the highest partial pressure for in the atmosphere, so even deionized water will have some nitrogen in, but we don't see nitrogen in anywhere else. We're just seeing it in this ejector, right, in high concentration. So that implies that there is a bit of CNO cycle going on in the structure here, but not in the way that the mainstream physics is suggesting it is. We got another one here which looks like 2 toroidal bits from inside, or maybe it's just one large toroid that's twisted into a figure of 8, which wouldn't be a surprise. And again, you've got iron and all of the elements that we're talking about here, some calcium as well. And here, this is the last one, and I like this one because it looked like the ARV, but I believe that this is the internal structure, based on its size, of a not very overpressurized substructure, or rather large structure. And it is the entire contents that's just come out in one little ball, and it has a little section on the top here, right? And so I looked at this, and unfortunately, oh no, oh, do I have it? Oh, maybe I don't. Maybe I do. Oh, I didn't save it. All right, well, it's in the video when you get the video. But trust me, it's all the elements. It's all of the elements you see here, all of them, right? In this structure that came out of the one of these things. So that, my friends, is the data from the last 4 days. Like I say, I will continue in the coming days to edit the raw captured microscope sessions, but we have a structure that is based on the sacred geometry, 100% certainly. This is not guesswork. It hasn't ever been guesswork, but this is the coup de grace, one might say, in terms of proving the case. And you can see exactly how it operates. You can see exactly the substructures, and one can imagine how it fractally goes down. You can see again how they link together in pairs. This one up here, you can see how the central torus is interacting with the substrate and leaving a hole there. And what this implies, really, that a normal tokamak will never work. It's a complete waste of taxpayers' money. I'm sorry. But I don't like anyone wasting life or money. And if someone's taking something out of your pocket to pay someone else to do something that's a complete waste of time, probably they're taking your life, because in my view, money is life exchange tokens. And so really they need to wake up to the reality that nature just wants to do this. And many researchers that have been working in the low-energy nuclear reaction fields have actually demonstrated this over and over again. But they've had all kinds of theories, and really, our ancients knew this already. They already knew how this worked, and we are only playing catch-up here. But my God, what kind of quality of conclusive evidence. For me, I will reiterate, for me, this has been a beautiful journey. And I have so many people to thank. All of the former directors of the MFMP, Matthew Villat, Nicholas Chauvin, Tyler Hooligan, Ryan Hunt. I have to thank particularly Alan Goldwater. In this place where we are right now, so many significant experiments have been done. And in fact, it was at this very table where I'm giving the presentation now where Alan brought in the indium sample. In fact, the indium sample in question, I think, is even in this drawer still. I think it's here, that showed me, it's actually it's here. I think it's this sample here, the before and after sample. And it showed me the first ohm symbol, or 3 ohm symbols, in which this coherent matter process occurred, and allowed me to how should we do this? It allowed me to what do we do? I'm going to put that down there. So I just want to leave those images up because I think they're just that they say it all, really. They allowed me to come down this journey, combined with the work of the late Neil Crichton Gold, and combining with the work of Suhas Ralkar, and the work of Dr. Ueshin Amasa, and the work of Takahaki Mashimoto to a degree, but to a huge degree, and Solin, and so many, Dr. Alexander Parkhomov, Professor Francesco Piantelli, Francesco Celani, so many contributions from the community, both in intellect and financial or logistical support. It's been a real honor, and like I said, I felt like crying, and I nearly burst into tears in front of Alan the other day, because I thought, I feel so lucky to have been put into a position where I could see this. And you guys are the first people to see this. And you've got the opportunity to make this happen. You have to get the word out. This has implications for just water flowing down pipes, but water flowing in streams. Water in movement is so much more special than just water in movement. It is literally creating the elements that we are comprised of, and that the land that we stand on is made of, from whatever. And it is the great yin-yang, it's the great balancer. I knew this was a deep responsibility, but I could never have imagined that I would get to this point.
So many people have sacrificed so much. So many people have had their careers ruined by the lies. It's the lies I can't stand, and the deaths of people for needless wars. Just stop the killing. We have a way forward. This technology allows so much. It allows so much to be possible. And anyone that is in any doubt, I ask you to reach out to Benjamin Huang and ask for a sample. And I mean serious people. I don't mean fly-by-nighters. People with the right tools. Because it's all there. The story is told by the one sample, just this one sample and the other sample, the two samples I asked for from his lab. And he was gracious enough to give to the project. The whole story is in just a few millimeters. That's it. You just had to look and open your eyes and see. My friends, we are at the dawn of an old age. We're not the most intelligent humans that have ever lived on this planet. This is working with nature, and nature is lazy. Humans are lazy. They want to get the most for the least effort possible, and nature wants to do that as well. And these structures that you see on the screen are able to do what we have been taught all of our lives is impossible. Transmutation of one element to another. And there it is, folks. The sacred geometry that underpins most of the world's architecture and is embedded in most of the world's religions to some degree. There it is. It's effortlessly balancing nature, keeping it in harmony, the yin and the yang, making elements where it's needed and desynthesizing where there's too much of one thing. It is a thing of immense beauty and immense significance. It is the great power. And we need to be careful with it because it is, as you can see, able to strip anything from anything. Nothing can contain it, but it's always been with us. It's always been with us in thunderstorms. It's always been with us in cavitation, in water, even in probably your house heating pipes, maybe. We need to respect it. We need to learn from the data that I've shared today, but also, this is just the beginning of the end. This really is the beginning of the end. I said that the beginning of the end in Japan in 2019, but really this is totally categorically certain knowledge in my view. I may be wrong. I have been wrong a lot of times in the past, but this cannot be coincidence because there are tens of thousands, hundreds of thousands, possibly millions of perfect examples of how this technology works right on this particular sample I have on the SEM right now. The question is, what are you going to do to make this happen? I've done as much as I can. Up to now, what are you going to do to make it happen? Each of you has a voice. I'd like to remediate waste, but, propulsion, it can do that too. It can do a lot of magic, this stuff. And you can't make it better. You cannot make it better. There's no means to make this better. It just does. Let nature do what it wants to do. This is negentropy, but it's also yin and yang. It is something that is able to destroy totally and something that's able to create. I can't do a quick summary of this. You'll have to go back. I need to focus on taking a walk and maybe editing the other raw material. But again, I want to thank Alan Goldwater for lending me his SEM, for the people that made this trip possible, Binja Huang particularly, all of the other scientists that I've worked with over the last more than a decade. This is it, guys. It's been done, but it's just the beginning. It's a tool which gives us the God's little toolbox, little g, God's toolbox. And may we use it wisely. With that, I'll say thank you, good night, buenas noches, dobranoc.
Thank you, President Lin, for